no, it's pretty good. Okay, looks like a good time to start. So what did you all think of the last homework? Uh-huh. Okay. Uh-huh. Uh-huh. Yeah. Certainly teaches a bit of patience. Okay, so let's just first review what's in our toolbox so far to set up what we're going to go through in this class. So a few weeks ago, we went through policy gradient methods, which are methods that estimate the gradient of the expected return of the policy. And all we talked about is how to estimate the gradient, how to get gradient estimators. Then we talked about methods that try to learn a Q function. In particular, they try to approximate Q star, the Q function of the optimal policy. And then we had a bunch of other, then Chelsea had a bunch of classes on model learning and so forth. But this is going to be back in the same genre as the policy gradients and the Q learning classes that I did a few weeks ago. It's going to be, we're going to talk more about model-free reinforcement learning methods. And so if you think about the policy gradient methods and the Q learning methods, there's sort of a difference between these two classes. So in policy gradient methods, we just talked about estimating a gradient. We didn't talk about having some objective function that you're going to optimize, except for the expected return of the policy. But that's an objective that we don't really have access to this objective in analytic form. We can just get estimates of it by sampling trajectories. Then in the Q learning section, we did have an objective, which was this Bellman error. So it kind of looked more like the usual kind of optimization problem you solve when in machine learning. So the topic of this class is going to be how can we reduce policy optimization to a optimization problem where you have some objective that you're going to optimize. And we're going to talk about a few different algorithms. And actually, the point of this class is both to introduce those algorithms and also just to introduce some new ways of thinking about about optimizing policies. So ways to think about this reduction from reinforcement learning to optimization. And that's really the key thing in deep reinforcement learning. So deep learning is all about trying to reduce learning problems into optimization problems, into nonlinear optimization problems where you have your neural net parameters and you're trying to minimize some loss. And the idea is that if you make everything differentiable and you choose a good model so that your problem is well conditioned and your model is expressive enough, then you can actually solve these problems that would otherwise look intractable and where you're trying to learn a complicated function. So to make deep reinforcement learning work, what we have to do is somehow reduce reinforcement learning into an optimization problem. And we've seen several different ways of doing that so far. That's sort of what the whole class has been about so far. But now we're going to dig more into optimizing policies and how to think about that as optimizing some objective. Okay, so first let's just write out our problem. We're going to define eta of pi as the expected return of policy pi. We're sampling the initial state S0 from our initial state distribution, rho 0. And then each time step, we're sampling an action using our policy pi. And this class, we're going to consider the discounted sum of rewards, the discounted return. OK, so let's say we have a policy which we're going to call pi old, meaning it's our old policy that we're going to try to update on. All we can do is we can sample from this policy. So the general framework is going to be we're going to sample from pi old, and then we want to optimize some objective to get a new policy pi. So how do we do that? Well, first, there's a very useful identity, which is that you can write the expected performance of a policy pi in terms of the advantage function of pi old. So the idea is you generate a trajectory using pi. Oh, this should say plus eta of pi old. So the eta of pi, it's going to be correct on the next slide, so I'll move on to the next slide. OK, so our identity is eta of pi equals eta of pi old plus expectation under pi of advantage function of pi old of the states and actions we reach. And this is this density. This actually refers to a sum over time. So we've got a we've got a sum over time that's like sum from t equals 0 to infinity of gamma to the t a pi old SA. OK, I was writing it in kind of shorthand form on the slides, but this is what the actual identity says. OK, so how do you prove that? So let's just look at this discounted sum of advantage terms. So each advantage term can be written as reward plus gamma times next value minus current value. So we start off with that sum. We write it in terms of the value functions. And then we realize that we have a telescoping sum. If you write out all these terms, you realize that most of them cancel out because state t plus 1 appears in this term and also the next time step. So most of these terms cancel out. And it ends up that all that's left over is the very first value function term. So we've got expectation of the value function at state 0, and then all of our rewards. So yeah, all of the other terms cancel out because everything else appears twice. Are
you assuming deterministic transitions here?
No, this isn't assuming deterministic transitions. So which step are you looking at?
We'll go into the second line. Show me like another expectation there.
Oh yeah, so that's a good point. So to go to this line, you do need to take an expectation over the time step t plus 1. However, we're taking an expectation over everything here. Like this outer expectation is over everything. So I skipped a step there, and you can sort of roll that into the outer expectation. So anyway, so this calculation just tells us that the discounted sum of advantage terms is equal to this, tells us the difference of the policy returns. OK, so we want to, OK, so that doesn't help us so far because all we have is, we can compute our expected, the performance of the policy using the advantage function. But we don't know, we still can't use this yet because the problem is that we have this state distribution. We have the states, we have this expectation over states sampled from the policy pi. And so if we're going to try to optimize over pi, then we can't compute this expectation at a new value of pi that we didn't we haven't tried out yet. So I mean, to estimate an expectation, you have to sample. I mean, since we don't have everything in closed form, the only way we can estimate this expectation is through Monte Carlo sampling. And so we don't have a good route to estimate eta of pi, to optimize over eta of pi. So what we're going to do instead is we're going to find a local approximation to eta. So, so what we do here is we define this objective called L, and we subscript it by pi old because it's going to also it's going to depend on the old policy that we're using for sampling, but it's going to be a function of pi, the new policy. So this is going to be an approximation of eta of pi, where pi is near pi old. So because we want to optimize eta of pi, but it hasn't. But since pi appears in the expectation, we don't have a good route to estimate this expectation at a new value. So we can't do that. So that's why we have to form this approximation L, where all the expectations are taken with respect to the old policy. OK, so what do we do here? So we just look. We have this expectation over S that we don't S is sampled from pi, which we don't like. So we just sample the states from pi old instead. So we just get rid of the term we don't like in the expectation. So we replace the expectation, the sampling from pi with sampling from pi old, and then we just use importance sampling here. So here, going from this expectation to this expectation, we replaced. We just said actions are going to be sampled from pi old instead of pi, but then since we're changing the distribution, we have to compensate for it by adding this importance sampling ratio. So and here, what we mean here is that we sample the states from the old policy, and then the actions are just used to compute this advantage term. So we're not accounting for how. I mean, when we say that the action is sampled from pi old here, we don't mean that you're generating the trajectory using pi old. We just mean that this advantage function term is that we're this expression inside the expectation is obtained by sampling from pi old. So anyway, so we wrote down this objective L, and this matches. So this gives you the right policy gradient when you differentiate it with respect to the policy parameter. So if you just look at L, you look at this expression for L, and you differentiate it with respect to the policy parameter, you get this. You can first write it like this, where you have the grad probability over probability, and then you can recognize that can be rewritten as grad log probability. Mm-hmm.
I think you can just only sample A from pi, or can sample S.
Oh, we can't. OK, the question was how can we sample S from pi? Can't we just sample A from pi? So we're sampling S from pi old, the old policy. If we wanted to actually sample everything using the new policy pi, we would have to actually sample a trajectory using that policy. So we would have to take actions in the MDP. Does that make sense? So the original.
So you mean like you generate a trajectory from pi old and you get a bunch of S and a bunch of A's and you sample the S from pi?
That's correct. Yeah. So if you want to sample if you want to sample everything using policy pi, you have to generate a trajectory with pi. But then we can't get a Monte Carlo estimate of eta of pi. If we want to do that, we have to actually execute the policy. But that's not so suitable for numerical optimization. All right. Let's see. So what is L here? it ends up being a local approximation to the performance of the policy. So we have our, we care about eta, which is the performance of the policy, and L is a local approximation to that. Okay. Mm-hmm.
So just kind of build intuition. So let's say, for example, you had an old policy, say from your pi old, and maybe let's say A of pi old for a particular A that wasn't really well that you didn't say with the high probability.
Yeah.
Pi old has a high advantage. Then eta of pi would do well for a pi that now gave more probability that that action that wasn't as strongly weighted before.
Uh-huh.
I'm just trying to get an
Okay, yeah.
how
Yes.
that would improve.
Yeah, let me try giving a little intuition for what L is. And also what eta, what this expression for eta means. So the advantage is telling you whether each action is better or worse than average. So this identity for eta tells you that if you want to figure out if policy pi is better than policy pi old, then you just look at all the states reached by pi and you see how much better or worse it's doing than pi old. It's like, let's say you have two runners in a race, and you want to know how much does runner A go faster than runner B in total. You can say how much faster does he go at this point in time, and how much faster does he go at this point in time, and you add this up over the whole duration of the race. So you could say, you could look at how much time he gains at each, or you could look at this along the track. So you could say we can divide the track into 20 different pieces, and how much does the runner gain in this part of the track? How much does he gain on the next part of the track, and so on. So the portions of the track here are like states. So this identity is just saying you look at all the states and you add up how much does policy pi gain on policy pi old at each state. And yeah, this is supposed to have plus pi old, eta of pi old here. So the advantage function is telling you the difference between the two policy performances. Okay, so that's just sort of the rough intuition on what eta, why eta has this identity holds on eta. So now what is L? So L, you're just saying I'm going to take the density according to the policy I sampled with instead of the new policy. And so this formula is saying, OK, we want to know how much better pi is than pi old. So what we're going to do is just look at all states reached by pi old, and you say how much does pi gain on pi old at each of those states. So if pi old is taking better actions at every state, or if pi is taking better actions at every state, then it's probably going to have a better cumulative reward. And so if you add up the advantage contributions from all the states, you get the total difference in performance.
So you're saying in general it's better to have the states be sampled from pi old as opposed to pi?
Right. So the question is it better to have states be sampled from pi old rather than pi? So the reason we want the expectation to be over pi old is because we want to construct some kind of objective that can be estimated using samples. And we're going to get samples from pi old. But pi is the new thing we want to, like, it's a new candidate policy that we've never executed before.
Okay, so there's no samples from that.
Right. Yeah.
Is it kind of similar to DQN when you have target network?
So the question was, is it similar to DQN where you have a target network? I guess you could, not exactly, but there's some similarity. Well, I guess there's some similarity because you could say DQN is sort of doing a batch. It's doing something like value iteration with a batch of data where you had the target network and now you're trying to do an update to the Bellman backup on that target network. So in the same respect, we're considering doing a batch method here where pi old is kind of like the old, it sort of corresponds to the the target network, which is the old network, and now we're trying to construct a new network pi. Yeah. Okay, so we know that we just showed that L is a local approximation of eta. So is it a good approximation or a bad approximation? Well, we know that it's right to first order. So it's if you just make an infinitesimal change to the policy, it's going to give you a good approximation of the change in the policy performance. So now there's actually, you can do some theory and bound the difference between L and eta. So I won't go through all the theory, but the result is that that you can put a lower bound on eta. So you can say that so you can construct a pessimistic approximation to eta, where it equals L minus some penalty, which looks at how much different the policy pi is from the policy pi old that you used for sampling. So this is saying that, well, I'll show a little plot that'll make this a little more clear. So let's say our true objective is eta. So that's the red curve, and we're trying to maximize it. So that's the performance of the policy. And then if we were to we can make this local approximation to the performance of the policy called L. That's this green curve over here. So if we take a tiny step, L is going to give a pretty good approximation to eta. So it has the same slope as eta. But if we totally maximize L without any constraints, then we'll end up all the way over here. And eta probably got a lot worse if we did that. So it turns out that by this inequality, we have this inequality that says that if you add a penalty term that penalizes moving theta away from theta old, then then we don't know how good the policy is going to be. So we're going to penalize the policy for that. So we add this penalty term, and we get this blue curve. And the theoretical result says that there's a bound. It says that this is a lower bound on the true performance of the policy eta. So it says that this expression is a pessimistic approximation to eta. And that's really good, because now let's say we maximize this blue curve, we optimize this pessimistic approximation, then we're guaranteed to improve eta, because the blue curve matches eta at the starting point, and it's always lower than eta. It's always lower than eta. So the improvement to eta is at least as good as the improvement to our approximation. So if we make this much improvement to our approximation, then we're going to make at least that much improvement to eta. So this is the general idea behind a minorization maximization algorithm, sometimes called majorization minimization. So the EM algorithm is also in this class. You make an approximation to your log likelihood, and then you make a lower bound to it, and you maximize that lower bound. So we're doing the same kind of thing here. Okay, so let's just look at this this bound again. So the problem with this bound is that it has this max over states S. So that's not so good if we want to do Monte Carlo estimates, because we're going to collect we're going to get a bunch of states, and we're going to construct some kind of objective. And if we have a max there, then our optimization is probably going to ignore all the states except one of them. Max is differentiable almost everywhere, but it's not so good for optimization if you have a max over all of your samples instead of a mean over all your samples, because only one of the samples is going to be active if you do that. And it also ends up being a really a more expensive optimization if you have lots of constraints instead of just one constraint. So we're going to make an approximation to this, and we're going to use a mean over states instead of a max over states. We're supposed to maximize this expression involving a max over states, but instead Okay, so we're going to make a bunch of approximations. First of all, we're going to sample. We're going to use sampling to get all of our states instead of. So we're going to replace an expectation by a Monte Carlo estimate. So here we're L hat. That just means we're taking a Monte Carlo approximation to L by collecting samples, and if we just need the gradient, then we don't have to do this probability ratio. We can just do the log probability instead, because it has the same gradient as the probability ratio. And then we use the mean KL divergence instead of the max. So instead of having a max over state space, we have a mean over state space. Okay, so what does that mean? We have, so we're going to just introduce a little more notation, and we say that we have this bar KL with pi old in the subscript. That means that we're going to sample states from pi old, and then we're going to take the average over. We're going to take the expectation over this state distribution of the KL divergence between the old policy and the new policy. So, so this is just saying we look at all the states and we look at the KL divergence between the old policy and the new policy at these states, and we're going to take that expectation. And we're going to do a sample-based estimator of this KL divergence. Also, the theory results in a certain constant C, but this constant is too pessimistic. It ends up giving you really small steps, and it only provides a guarantee for the discounted return. That you're going to, it provides a guarantee that you're going to improve the discounted return, but we don't actually care about the discounted return anyway. We usually want the discount to equal 1. So it actually doesn't provide us with a very useful guarantee. Instead, we're going to use a fixed coefficient that we determine heuristically or an adaptive coefficient. And then we're going to talk about another algorithm called TRPO that uses a hard constraint on the KL divergence instead of a fixed penalty. Yeah.
So here, when you substitute with the mean, the bound might not necessarily, the original bound that you're using
Yeah.
might not hold, right?
Right. Yeah, so the question is, if you use the mean instead of the max, then the original bound might not hold. Yeah, that's correct.
So, so why is this justified then?
So it's not theoretically justified. There are some other ways of deriving, there are other heuristic ways of deriving the mean. And it turns out that if you do a lot of different things, it points in the same direction, which is to use the mean KL divergence. Another justification is that you can look at the KL divergence between the trajectory distribution of the old policy and the trajectory distribution of the new policy. And then the KL divergence between the trajectory distributions is just the sum of the KL divergences at each time step. So that's another way of getting it. But yeah, it's not totally justified. Mm-hmm.
So is there any reason to believe that like the max over the states, so that'll be a good approximation of mean when there's like one dominant state
Mm-hmm.
that has like a lot of mass?
Yeah.
Is there any reason to believe that that might be true, or do you think that's not even true?
Okay, so the question was, when is the mean a good approximation of the max? It seems like it would only work if you have one state that's sort of dominating this average. Yeah, that's correct. So you can actually look empirically at what's the max KL divergence. When I try to optimize this objective that involves the mean KL divergence, and you'll find that the max is usually actually pretty big, and it violates. Well, it's much bigger than the mean. Yeah, but it turns out that that doesn't matter so much empirically. Yeah. Okay, so how do we actually solve this? Okay, if you didn't understand some of the justifications before of why we want to write down this surrogate objective, that's okay. I mean, this part is, you can just assume that that's the objective we're going to get, and the next part should make sense. Because now, from this point on, we're just going to talk about numerical optimization. So we're going to assume that we constructed this objective, this surrogate objective L, which just involves probability ratio times advantage function. And then we're going to do numerical optimization with respect to the policy parameters on L. So this is like we just collected some data with our policy, we constructed the loss function, and now we're going to do numerical optimization on it. So we want to maximize this, this penalized objective, which is the surrogate loss minus some coefficient times the KL divergence. And what we're going to do is make a linear approximation to the surrogate objective and a quadratic approximation to the KL divergence. So this is often what you do when you have, this is, in a lot of numerical optimization, you construct a series of subproblems where each subproblem is easy, where each subproblem is an approximation of the original problem that is locally valid around your current iterate. So that's what we're going to do here. So the linear approximation to the surrogate L is just, it's just our gradient of L times the change in theta. And then we're going to construct a quadratic approximation to our KL divergence term. And so that ends up, we can write that as a quadratic, that's just a quadratic form. Or that's just this quadratic term here. The reason it doesn't have a linear term, that we don't get a linear term from the KL divergence, is that the KL divergence is minimized at the starting point that we're linearizing around. So, so the linear term vanishes because the gradient vanishes at the minimum of a function. So, so this is our quadratic approximation to the objective. There's also a quadratic, if we really wanted to make a quadratic approximation to the objective, there would also be a quadratic term coming from L. But we're going to omit that term because it ends up being negligible compared to the quadratic term from the KL divergence. And because if we included that, our objective, our f would no longer be positive semi-definite. Because if you take some function and you take the Hessian, it's usually not, I mean, if the function isn't convex, it's not positive semi-definite, and there's no reason to believe that L is convex. However, the KL divergence, when we take the Hessian of the KL divergence, this is positive semi-definite because the KL divergence is minimized at our starting point where theta equals theta old. So, I mean, if our objective weren't positive semi-definite at this point, then there would be some direction where you can go down to negative KL divergence. But it's minimized when the KL divergence is 0, which is at theta equals theta old. So there can't possibly be any, so it has to be positive semi-definite. So, okay, yeah, we're going to ignore the other terms. And the solution you get is, well, you just get a solution by setting the derivative to 0 and solving. And you get the theta minus theta old is just this 1 over this constant times F inverse G. So this is just a Newton, this is just a usual Newton step. Okay, so we got that our policy update should be of the form constant times F inverse G. But we don't want to form this full Hessian F because let's say we have, let's say our policy has 100,000 parameters. We don't want to form a 100,000 by 100,000 matrix. Even if our policy has 1,000 parameters, so we could easily form a 1,000 by 1,000 matrix, that would be really computationally expensive because that would be like we would have to compute 1,000 different gradients. Like if you want to compute a Hessian, the computational cost is going to be number of parameters times the computation cost of a gradient. So computing Hessians is really expensive. So we definitely don't want to do that. What we can do instead is we can compute this step approximately using the conjugate gradient algorithm without forming our Hessian matrix explicitly. So this is actually a pretty common, this is actually a useful optimization tool which appears in a lot of different places. So I think even if you don't use this in reinforcement learning, it's worth knowing about how to do how to do these kind of this kind of second order optimization, and I think it's it's not necessarily that well known in all fields. It's well known in some fields, but not others. So this is going to be called the truncated Newton method. You can find it in any. You can find this in like any numerical optimization textbook, like the great textbook by Nosidal and Wright. So if you want to learn more about how to use conjugate gradient algorithm to solve numerical optimization problems, I recommend that particular book. So what does the conjugate gradient algorithm do? What it does in general is it solves linear systems approximately. So let's say let's say you have a matrix A and a vector B. Conjugate gradient algorithm is going to approximately compute A inverse B, which you can also think of as the solution to AX equals B. But the really nice thing about the conjugate gradient algorithm is you don't ever need to form the matrix A. So with other methods for solving linear equations, you need to form your matrix, and then you need to do some kind of like reduce it to row echelon form or something. If you've like looked into numerical linear algebra, it works by doing some kind of matrix factorization or by doing a series of like subtracting rows and stuff. So usually if you want to solve, the way people solve linear systems is they do a bunch of operations on the matrix. But the conjugate gradient algorithm never forms the matrix. It only reads the matrix by computing matrix vector products. So it takes vectors V, and you have to be able to compute the matrix vector product A times V. I won't go through the whole conjugate gradient algorithm, like explain the algorithm and everything. I'll just say that what it does is, after k iterations, it's minimized this quadratic form, 1/2 x transpose ax minus bx, in a certain subspace, which happens to be the subspace spanned by b, ab, a squared b, and so on. So it solves, it minimizes a certain quadratic form in this subspace. So as the iterations go to infinity, it exactly solves, or not infinity, it has to go, if you do this, if k equals the dimension of x, then you exactly solve this linear system, and you get A inverse B. But we're just going to treat conjugate gradient as a black box that approximately computes A inverse B. So now let's talk about how to use this for optimization. So that's conjugate gradient algorithm for just solving a linear system. But how do we use it in optimization? So let's say we're optimizing over our parameter vector theta. So we need to do Hessian vector products to be able to do the conjugate gradient algorithm. So what we want to do, okay, so in optimization, what we're going to want to do is compute we want to do H inverse V. So if we have a vector V, we want to be able to compute the Hessian inverse times V. So in particular, if we want to do a Newton step where we take the gradient, V is going to be the gradient here, and we want to take Hessian inverse times gradient. So the question is, how do we do that with conjugate gradient algorithm? So to do that, we need to be able to compute Hessian vector products of the form, we want to be able to take a vector V and compute the Hessian vector product HV. So it turns out you can do this in just a few lines of any autodiff software like TensorFlow. So the way you do it is, let's say you have your parameter vector theta. Then you construct your scalar loss function. So let's call that f of theta. Then we just make a variable for the vector that we want to do the Hessian vector product with. We compute the gradient. So we compute the gradient symbolically. Then we form symbolically the gradient vector product. So that's just dot product of gradient with our vector. And then we differentiate the gradient vector product to get a Hessian vector product. So we just formed our Hessian vector product symbolically. And this is just a gradient. So, I mean, if we wanted to form the full Hessian, we would have to take the gradient, and then we take the gradient of that. So we would take the gradient vector, and then we do the gradient of that to get a matrix. But that would be really expensive, because the only thing you can do efficiently is to take the gradient of a scalar. But to do the Hessian, that's expensive. Backpropagation just computes the gradient of a scalar. So the nice thing here is we're forming this scalar, which is the gradient vector product, and then we differentiate it to get the Hessian vector product. And so this was all these efficient operations, which are gradients of scalars. And it turns out that to do this Hessian vector product, it's only 1 to 2 times as expensive as computing the gradient of our loss function f of theta.
So in the fourth line, when you take the gradient, that's also with respect to f of theta, right? Or is f another thing?
In the fourth line, oh yeah, sorry, that should say f of theta. Yeah. Okay, so that's what you do in general if you want to do a Newton step, which is Hessian inverse times gradient. So how do you do that if f happens to be the KL divergence between our new policy and our old policy? So here's just sort of what the pseudocode looks like for that. What you do is you let's say we have a network. We have theta is the parameters of our policy. Let's say theta is like the flattened all the flattened weights and biases of a neural network, and then we're gonna reshape it and slice it and everything to put it into our neural network. But let's say theta is just a flattened out vector of everything. So we're going to use theta and then apply the neural network that's parameterized by theta to get action probabilities. So let's say this is a symbolic expression for the action probabilities. So this is going to be a matrix where there's batch size times n actions elements in it. So what you do is there's a trick. We're trying to compute the. What we could do is we could compute the action probabilities numerically and then treat them as a constant and plug that into our numerical calculation. But what we can do instead to get the same result is to use a stop gradient operation, which just tells the automatic differentiation software that it should pretend this is a constant after it does the forward pass. So this is just a trick that you can use with TensorFlow or Theano or probably any other autodiff software. So you do this stop gradient, and then you construct the KL divergence. If you have a discrete distribution over actions, the KL divergence will be something like you know the expression for KL divergence, which is like sum of probability times log of the probability if over the other distribution. So this is KL between P and Q. If these are two discrete probability distributions. So you construct this KL. You construct this KL divergence. Oh, and this should be a sum over all axes. So this is a scalar. So you construct we should take a mean over the 0th axis of this. So we're taking a mean over the batch of the KL divergence. So that's our scalar loss function that we're going to use to compute the Newton step. So we compute the gradient and then the gradient vector product and then the Hessian vector product. All right. So in summary, so we want to solve this KL penalized problem. So we want to maximize this expression, which is of the form loss minus KL divergence. So we make a linear approximation to the loss and a quadratic approximation to the KL divergence term. So then we get this. Now we're maximizing this quadratic form, and what we get is that our step is just 1 over constant times f inverse g, where f is this second derivative of the KL divergence, and g is the gradient. Since we are never forming f explicitly and we're not solving this exactly, we're going to solve for this term approximately using conjugate gradient algorithm by forming the Hessian vector product function and then using that for the conjugate gradient algorithm. Okay, so that's so this is can be called the truncated natural policy gradient algorithm. And the way it works is, so you run your policy to collect time steps or n trajectories. You estimate the advantage function at all time steps. Then you compute the policy gradient. Then you do conjugate gradient using Hessian vector products to compute this step of the form H inverse G. And then you scale it by a step size alpha so that your new policy is obtained by taking your old policy and adding this term alpha H inverse G. Any questions? All right. Let's see. Should we take a break now? Yeah, it's about a little more than halfway through, so let's take a break. If you have any questions, you can come up and ask me about them, and we'll start again at 12:05. Mm-hmm. Yeah. What you want to go back to the
Yeah, I
slide?
just want to take a look at it. So this thing, I mean, okay. First, well, you could have just done like simple gradient descent, right? And the algorithm would still be the same, except that your gradient wouldn't be as, I guess, optimal.
You could do gradient descent on the quadratic form.
Right.
Yeah, you could do that.
Okay.
Yeah, that would just be less accurate.
Right. Okay.
Yeah.
So that like the gradient part is kind of like plug and play.
Mm-hmm.
Then now for you, can you show me this whole trick that you did with the Hess, like the sum product, the vector sum product?
Mm-hmm.
How does that work again?
Okay. Yeah, that's a neat trick. So let me go back to that. Let's see. Let's see. Here it is. Okay. So the idea is that we can take gradients of scalars. If we have a scalar, we can compute the symbolic gradient of it. And then to actually numerically compute the gradient of the scalar, it's still cheap to do. And it's going to have computation time that's only a small constant factor times the computation time for computing that scalar.
Right.
Okay, so that's like the cheap gradient principle. That's what it's sometimes called. So now we want to compute a Hessian vector product, but we never want to form the Hessian because we can't. That's expensive. It's expensive to form the Hessian. So
because it'll go as n squared.
That's right. Yeah.
Okay.
Yeah. So what we're going to do is instead cleverly try to compute it by constructing a scalar and then differentiating that. So we first construct a scalar of the gradient vector product, and then we differentiate that to get the Hessian vector product.
Okay. So you take the gradient, and then you take the dot product of the gradient and the vector that you're and the vector. What vector is this?
This is just an arbitrary vector that we're going to that conjugate gradient algorithm is going to give us that vector. So conjugate gradient algorithm is going to pick a series of vectors and then plug them into this this expression.
Okay,
Yeah.
I see. And these vectors would have been this B, A, B, A squared, B.
Mm-hmm.
Okay, because I guess in general, what this would give you is H inverse, or the Hessian inverse, times one of these vectors from this subspace.
It's going to give you the so it's going to solve for this system in the subspace. It's
Okay.
going to find the best vector in this subspace.
Okay, I see. And then now when you get that vector, then you would evaluate H inverse V. H inverse V would happen at, V would be the vector you're getting from this.
V is actually, so
it
V is
HV?
you're trying to solve for H inverse V. So you're solving the equation H times like X equals V.
Okay,
So
I see.
yeah.
Okay, so
So you're
now-
solving for X.
I see.
Yeah.
So then there's a gradient.
H is like A is associated with H here.
Okay, I see. So then now when you have the gradient times the vector, that vector would have been X in this case. Or?
Yeah. So the vector here is actually yeah, that's right. So that well, it corresponds to V here.
Okay.
So
And V is what it's solving for. So it's solving, like, so this vector is not known yet.
this vector is, we're going to come up with a series of these vectors. So conjugate gradient algorithm is going to, it's going to generate a series of vectors and then ask for the Hessian vector product,
Okay.
or the matrix vector product.
And then when you do this multiplication, this is element-wise multiplication.
Yeah, so I wanted to do the dot product. Yeah, this is just the dot product, gradient
Okay.
dot vector.
Oh, I see. So, okay, so then you do the dot product. Then now once you have the dot product, you can now compute the gradient again of that, and that will give you the Hessian.
That's right, yeah.
Oh, okay. So, or actually, that would give you the Hessian times the vector.
Right.
Okay. I see, I see. Okay, yeah, I
Mhm.
see. All right, great. Thank you.
Mhm. Mhm. Yeah.
Expression, what is actually the update for the conjugate gradient?
Oh, so what is the conjugate gradient to?
Well, what's the update?
The update. I don't quite understand.
In this TensorFlow code? What
Oh,
is in the
oh, I see. So then you're gonna evaluate the. You're gonna write something like CG of like Hessian. You're gonna have a function that computes the Hessian vector product numerically. Let's call it compute HVP, and then you plug in the policy gradient G. So you're going to take the an implementation of the conjugate gradient algorithm that numerically performs the conjugate gradient algorithm, and you're going to plug in this this compute Hessian vector product function and the numerical gradient. So this part is happening in numerical land, and everything here was in symbolic land. Yeah, that's a good point. Actually, I'm going to say that to the class also, because that's a good question. Yeah. Okay, time to get started again. One point I'll make about this calculation right here is, so this is showing you how you can get a symbolic expression for the Hessian vector product. So now the question is, how do you actually use this in your numerical code to update the policy? So what you're going to end up doing in practice is you're going to take this expression for the Hessian vector product symbolically, and then you're going to use that to get another function that computes it numerically. So let's say you have a function called compute HVP, which computes the Hessian vector product numerically. Then you're going to plug that. Then you're going to plug that function along with a gradient vector, a numerical gradient vector, into a numerical routine that performs the conjugate gradient algorithm. So you're going to just have a generic implementation of conjugate gradient, which uses a matrix vector product and a vector, and it's going to compute it's going to solve approximately for A inverse G, where A is the matrix you're multiplying by, and G is the second argument you're passing in. So you have so compute HVP is taking a vector v to HV, and when you plug that in along with G into the conjugate gradient function, then you're going to get something that's approximately equal to H inverse G. And the approximation will become more and more accurate as you do more and more iterations with conjugate gradient. And what conjugate gradient is going to do is it's going to come up with a series of vectors v, and then it's going to plug them in it's going to plug them into the Hessian vector product function. So v here is going to there are going to be many different vectors. There's going to be a vector passed in at each iteration to our Hessian vector product function. So conjugate gradient is going to come up with a series of vectors and query at those vectors for what the Hessian vector product is. Okay, so that's the truncated Newton method, which is a general optimization technique, and you can use that here to do natural policy gradient. It's called natural policy gradient for reasons I'll describe in a few slides. But the point is, okay, normal policy gradient, you just update by adding alpha times G. Here we're adding, we're using this this matrix H to compute the step direction. So we're doing H inverse G instead of G. So it's like a second order optimization method instead of a first order optimization method, because we're computing something like a Newton step instead of computing a gradient step. However, we're not actually using the Hessian of our objective. We're using the Hessian of the KL divergence, and the reason is because we constructed this this objective that has surrogate loss plus KL penalty, and the KL penalty is saying don't go too far away from where you started, don't change your policy by too much, and that term is dominating the quadratic part of our objective. So that's sort of the main term in the Hessian, and that's why we can use it to compute our second order step. Okay, so there's another variation on this called trust region policy optimization, or TRPO, where instead of solving the n-constraint problem where you have a KL penalty, you solve a constraint problem where you have a hard constraint on the KL divergence. And actually, it's only a tiny modification. So all you have to do is you have to rescale the step you got from the previous method. So you just have to shrink, or you just have to rescale your step by some constant, by some scalar. So the unconstrained problem we were solving before was we want to maximize the surrogate loss minus KL penalty. So now the constraint problem is going to be we maximize subject to a constraint on KL divergence. And okay, why do we want to do this constraint problem instead of the unconstrained problem? Often it's easier to set the hyperparameter, which is the KL divergence between the new policy and the old policy. rather than setting this coefficient c. I mean, one way you can see that is that if you rescale the rewards, that's going to change the scale of the surrogate loss term L, but it's not going to affect the KL divergence. So, so you would have to rescale. So the solution you get is going to depend on the scale of the rewards, or C is going to depend on the scale of the rewards if you use the penalized formulation. But in the constrained formulation, you don't care about the scale of the rewards because that's just like a fixed constant in front of your objective. But you have a hard constraint, so you don't have to worry about the relative, how to weigh the objective versus the KL penalty term. So that's the main benefit of using the KL penalty. Also empirically, you can use a fixed hyperparameter for the whole optimization process when you're using a hard constraint on KL divergence, whereas there's often no fixed value of C that works for the whole optimization process when you're trying to learn a policy. So you initialize with some policy, and then you do an iterative method, and it turns out that if you have a fixed value of C, then at some intermediate iteration, you might end up with a really big step that's bad and messes up your policy. Okay, so how do we solve this constraint problem? So again, we're going to make a linear approximation to the objective and a quadratic approximation to the constraint. So now we have a constrained quadratic problem where, so now we're trying to solve the quadratic program where we want to maximize gradient dot producted with theta minus theta old, subject to the quadratic constraint theta minus theta old 1/2 times theta minus theta old transpose times, are we calling it H or F here? H times theta minus theta old is less than or equal to delta. This is just our hyperparameter. So that's, we're taking the linear and quadratic approximation. So the way you solve these constrained optimization problems is you write down the Lagrangian, and the Lagrangian has to be 0 at the solution. I mean, the gradient of the Lagrangian has to be 0. So we write down our Lagrangian, we differentiate it, and we get that the solution has the form H inverse G scaled by some coefficient. And that's just like we got in the unconstrained problem. So in the unconstrained problem, we got H inverse G scaled by some coefficient. So now we just have to figure out what's the coefficient to put in front of H inverse G so that we get the appropriate step length. And to satisfy this constraint, we want this quadratic term, this quadratic approximation to the KL to be equal to delta. So we want to scale our steps so that we get the right, this term has the value delta. So what you can do there is you can calculate exactly how much you should scale it, and it turns out to be this expression here. So if we have a step, the unscaled step, so we have H inverse, we just take H inverse times gradient to get our unscaled step. Then we can rescale it by just multiplying by this coefficient, which is square root of 2 times delta over the old, over this quadratic form, unscaled. So Hessian times unscaled step dot producted with the unscaled step. So this can be, this term in the denominator can be computed with the help of just one Hessian vector product. So if you do one Hessian vector product, you can compute this HS, and then you can dot product that with S. So all you have to do is rescale the step. All we're doing here is rescaling the step so that the constraint is exactly satisfied, and so it's tight. So just to summarize, we compute our unscaled step, F inverse G, and then we rescale it. That should say H inverse G. So we compute H inverse G, then we rescale it, and we do the then we do a backtracking line search on the original problem to try to find improve our objective subject to the constraint. So note that we made a quadratic approximation to the problem, and that might be a really bad approximation, but we use that to compute a step direction. So now we want to just make sure that we're going to compute a step that actually improves our objective and satisfies our constraint. So to do that, we just do a line search on the a line search on the objective.
I have a question. Have you ever tried considering like a soft constraint on the what's it called, the delta right there? For the KL divergence instead of just a hard constraint?
So the question was, can you do a soft constraint instead of a hard constraint? So what would so do you mean like
SVM kind of type of thing.
Okay. So you could do a penalty instead of a constraint. So that's sort of what we were doing before. And you could do other kinds of penalties like L1 kind of penalty instead of a, yeah, you could maybe do other kinds of penalties. But yeah, there are a lot of possibilities here.
Is there anyone that so this one works empirically the best?
This one works pretty well empirically. There are a bunch of things that work well empirically. Yeah. Okay, so you do a line search, and so the whole algorithm looks like this. You run your policy for t time steps or n trajectories. You estimate the advantage function at all time steps. You compute the policy gradient. Use conjugate gradient to compute the H inverse G, the Hessian. This is like your step direction. And now here's the difference between the truncated natural policy gradient algorithm. The difference is that you rescale the step by doing a line search, and you rescale the step so that you satisfy your hard constraint on KL divergence instead of just using a fixed scaling that's constant over the whole optimization process. So that's the only difference. And then you apply the update. So the only difference between this and the algorithm a few slides earlier was that we rescale the step differently. Any questions? Okay, so actually, this was not historically the first. People have been doing this idea of using what's called a natural gradient instead of taking the policy gradient is actually pretty old. I'll show some citations in a couple slides of where you can find the original papers on this. But this is a pretty old idea, and actually the technique I just described of using conjugate gradient and thinking of it in terms of a KL constraint is actually a newer way to do this. But the older way to do it is you can compute this matrix you can compute the matrix H that we were talking about earlier in a different way. So the idea, to explain the idea, let me just go back from reinforcement learning to a more general setting of parameterized probability distributions. So let's say we have a parameterized density p sub theta of x, and we have a so now we're going to talk about this concept called the Fisher information matrix. You might have heard of it in other kinds of areas of statistics and machine learning. But just to review, so if you there are two equivalent expressions for it. One is that you take the grad log probability. You take the expectation of the outer product of grad log probability with itself, or equivalently, the covariance of the grad log probability. So that's one way of writing the Fisher information matrix. The other way is you take the KL divergence between the probability distribution and some new probability distribution. So you take the KL divergence between P sub theta old and P sub theta, and you evaluate that at theta equals theta old, and that gives you the same Fisher information matrix. In both sides, we have to evaluate at theta equals theta old. Otherwise, it's not true. Okay, and the way, so the nice thing about this, I mean, when you note this equality, this shows that you can, instead of taking the second derivative of the KL divergence to compute this matrix H that we were talking about before, we can instead compute grad log probability at a bunch of states and take the outer product of it with itself. So we're getting like second moments of grad log probability, and we're using that to compute our update. So now in the policy optimization setting, instead of forming our matrix, our Fisher information matrix by differentiating KL twice, we can form it by taking the gradient of the log probability and doing the outer product of that and summing those up, or actually taking the average. And this is the same gives us the correct expectation. It's going to give us a different finite sample estimate, but yeah, it has the correct expectation. It's a little higher variance, but
So if we're evaluating at theta old,
mm-hmm.
then so this doesn't depend on theta at all?
So we're just, okay, so the question was, we're evaluating at theta old, so does this depend on theta or not? So the reason why we have theta in these expressions is because we're differentiating with respect to theta, but we need to make it clear that so the derivative, that some arguments of the expression are fixed and some of them are variable and are going to get, or we're going to take the derivative of. So we take the derivative pretending that these two, that theta is different from theta old, and then we set theta equals theta old after taking the derivative. So basically, the reason why we have to create two different variables and then reintroduce, then we say they're the same at the end. That's because we need to be explicit about what the derivative is going to hit inside of these expressions. Any other questions? Or does that make sense? Okay. Okay, so that's those were a bunch of different ways of computing the a policy update by doing a step of the form Fisher information matrix inverse times gradient. So that's not the only thing. That's not the only sensible thing that you could do. So at the beginning of the class, we were talking about constructing this surrogate objective and optimizing it subject to a KL divergence constraint. So we can solve that kind of problem more explicitly. So that's what we're showing here, and this can be called proximal policy optimization. The idea is that you write out this objective, which is the sum. You take the probability ratio times advantage function minus our KL divergence evaluated at state at our state S sub n, and then so we construct this objective, and then we do we just collect a batch of data, and we do SGD on this objective for some number of iterations. And what do we use for our coefficient C? Because we were saying earlier that that's kind of finicky and hard to set. So you can just adjust this adaptively by saying that you run your SGD, and if the KL divergence is too big, then you need to increase the penalty. So you increase C, and if the KL divergence is too small, then you need to decrease the penalty. So you'll take a bigger step next time. So you adaptively adjust your coefficient on the KL divergence, and that ends up working well enough as a way of keeping like a roughly constant KL divergence each time you do an update. So it turns out that this much simpler algorithm has about the same performance as the trust region policy optimization, but it only requires first order optimization instead of requiring you to do this conjugate gradient with second derivatives. So actually, this is a good one to implement if you just need a good practical algorithm. Okay, so I just want to add make a little comment, high-level comment about what one way you can sort of interpret the material from this class, this particular lecture. So when you're trying to get some algorithm to work, it's useful to know all the approximations you're making, and so you can figure out what might be going wrong. So let's say you run your code and it doesn't work, then you're wondering why doesn't it work, or where did it go wrong? So in supervised learning, you're making essentially two approximations. The first approximation is you're doing gradient descent. So you're assuming that the linear approximation that you get to your function, the linear approximation to your function, which is given by the gradient, is a decent approximation over the region that that contains your update. So the gradient you can think of as just a linear approximation to your function, and you're using that to compute an update. And if the gradient, like, let's say this is your function, or let's say your function is like this, and you're computing the gradient here, and then you're doing a big update. It might be you're doing a big update. Actually, let's say your function is like this. Then if you take an update using the gradient, assuming that this linearization is correct, then you're not going to be happy. So that's the first approximation. And the second approximation is when you're doing stochastic gradient descent, you're using your training error, and you're assuming that that is a decent approximation of your test error. And in fact, in SGD, you're assuming that the mini batch that you're computing an update on you're sort of overfitting to your mini batch a little bit each time. So if your step sizes are too big, then it's like you're overfitting to the most recent data too much. So that's why you often have to reduce your step size over time. So, but basically there are two sources of error. There's the approximation error from the linearization, and there's the generalization error, because your step is just like overfitting to the most recent mini batch. Okay, so now in reinforcement learning, you have almost the same issues, except you have one extra source of error. So we're making a linear approximation to the performance of the policy given by the gradient of the surrogate loss. So that's the first approximation, but that's the same as what we had in supervised learning. If you think of the surrogate loss like the training error, which you're optimizing in supervised learning, then you're making the approximation that your training surrogate, which you use to compute the update, is a good approximation of the test surrogate, which is what you would get if you collected an infinite amount of data. I mean, you're going to collect a finite number of time steps and use that for an update, and you're hoping that that's representative enough that it's going to give you a correct update, as opposed to your policy is just overfitting to the recent batch of data that you saw. Okay, but the third approximation that you're making here is that the state distribution doesn't change too much. That when you're ignoring how the state distribution is changing due to your policy update. So the reason is that any kind of loss function that you form in policy optimization is using an expectation over the state distribution from your old policy. So you're using your old policy to sample some states, and then you're constructing an objective out of that. So you're going to inevitably ignore how the state distribution depends on the policy. I mean, it turns out you can account for that by using importance sampling, but that never actually helps in practice. Or it gives you really high variance, so that ends up being bad. So basically the problem is that in policy optimization, you're ignoring the mismatch you're ignoring how the state distribution is going to change. And that limits the size of the update you can make. Because if you were to do it too big of an update, then your policy would visit some totally different states that you've never seen before, and something bad might happen. So it's like, let's say you have a driving policy, and it's like it's always like drifting off to the side of the road a little bit too much. So it's like on the highway, when you drift to the right side too much, it starts buzzing a little bit because they've got some grooves in the road. And then you adjust the policy to turn more to the left. If you do too big of an update, now maybe it's just going to totally change lanes and drive like onto the other side of the road. So whereas if you just do a tiny update, you can be pretty certain that it's going to do the right thing and it's going to drive in the middle of the lane. Okay, so if you want to read more about some of these ideas, so the original paper that was proposing to use the Fisher information matrix to compute a better policy update, that was this Sham Kakade natural policy gradient. Then there was another paper that he and John Langford wrote, which did some nice theoretical analysis on that introduced this idea of the surrogate loss and analyzed like how much the surrogate loss differs from the true performance of the policy. So that's from this paper, this 2002 paper. Another take on the natural policy gradient is in this Peters and Schall paper, which also has some nice practical ideas on it. So I recommend that paper. Then there was a paper that my colleagues and I wrote where we sort of refined this a little bit and described how to use the conjugate gradient algorithm to do the updates. And then so some of my colleagues and I had a paper where we benchmarked some different algorithms, such as the TRPO and the truncated natural policy gradient, as well as some other algorithms in the literature. Also, there's this idea of using conjugate gradient to compute to optimize neural networks has been used elsewhere in the deep learning literature. So this paper, Training Deep and Recurrent Neural Networks with Hessian-Free Optimization, gives a good description of a lot of the tips and tricks there, and they have some nice practical advice. Yeah, all right, that's it for this class. Thank you.